This video is going to introduce you to the methods that allow us to obtain estimation models based on scaling laws. During sizing and optimization process, different types of model will be necessary. Estimation models. They permit to estimate from a reduced set of main parameters all the parameters necessary for simulation, for integration study, masses, dimensions, and for the validation of the component's smooth running. They substitute the use of catalogs when these are not available or when we want to explore design domains, such as scenario analysis or optimization. Simulation models, they give the possibility to compute power variables, powers, energies, and all other sizing quantities for each architecture's component. Evaluation models, they help to verify that each component will remain within its working limits and will last at least the lifetime required. We're going to study the establishment of these models thanks to catalog data. For preliminary design, obtaining components' characteristics can be necessary for simulation or the comparison of different possible solutions. This information can be obtained in catalogs if the component can be chosen from an industrial range and if the catalogs give the desired characteristic, by computing them using complex design models, by asking experts or subcontractors, but the answer can take a while to be found, by using models which extrapolate a component's characteristics from a known reference component. The last solution is the one we will develop using scaling laws. Scaling laws reduce the complexity of the inverse problem by using two modeling hypotheses on the input parameters. First, every material's properties are supposed to be identical to the ones of the reference component. Secondly, some dimensions vary in an homothetic way and can be expressed as scaling laws equal to the variation of one dimension, here L star. Because the number of input parameters has been reduced, it is easier to give the relations that link the useful parameters for the design phase to a small number of key parameters called definition parameters. The scaling law gives the possibility to modify a parameter for a change of dimension. It is necessary to have a reference component. In this example, we want to evaluate the winding resistance of a bigger motor than the reference motor. The size variation is L star. The resistance variation is R star. The concept of geometric similarity is really important for scaling laws. We're going to use the cylinder volume to illustrate it. Geometric similarity means that all of the object's dimensions change with the same factor. Therefore, R star equals L star, and the volume is proportional to the length variation to the power 3. The same way, the mass is proportional to the length to the power 3 and inertia to the length to the power 5. There are two ways to obtain scaling laws. We will demonstrate how to do it by calculating the thermal constant of an electrical motor. The first approach is the direct one, using known equations. The time constant is equal to the thermal resistance times the thermal capacity. The thermal resistance is inversely proportional to the surface of the heat exchanges, which means the length to the power minus 2. The thermal capacity is proportional to the mass of the system, that is to say, the length to the power 3. By multiplying these results together, we can determine that the thermal constant is proportional to the length to the power 1. In the second approach, we will use the Buckingham theorem to find the same results. We know that the time constant of the system is linked to the dimensions and to the physical characteristics of the components. We can reduce the number of parameters by finding dimensionless numbers as a combination of its characteristics. As the final parameter we found is constant, we can establish that the time constant is proportional to the length to the power 1. When a scaling change occurs, some non-geometric quantities can evolve and could lead to malfunctions at component level. For example, we will study the electrical motor and the gear reducer, which are the quantities that limit the transmittable torque. For an electrical motor, is the maximal temperature of winding. For a gear reducer, it's rather the maximal stress. In a general way, we must determine the sizing constraints, that means parameters, that limit the studied device's performance or lead to its destruction. This change in scale has then to be done with x equals constant or x star equals 1. Here, the temperature and the stress equal 1. Here's an example of application for scaling laws in the biology domain concerning the body mass of animals. This example assumes that the mechanical constraints that characterize the bones does not depend on the animal. Therefore, it's quite simple to establish a relation between bone's diameter and the mass the animal has to support. Here are two exercises concerning scaling laws. Exercise 1. Try to demonstrate the relation between torque and dimensions. Exercise 2. Answer the following question. Can we increase the diameter of a rotating device without changing its rotation speed? Try to express the relation linking the rotation speed omega, the volumic mass ρ, the diameter d, and the constraint sigma max. Demonstrate finally the relation between max speed and dimensions. Scaling laws. Ah, non, je l'ai déjà fait lui.